Hi everyone, welcome back to the Transport Phenomena class. Today we will discuss the first exercise in the mass transfer. In this case, we have a diffusion through a stagnant gas film. Here we have liquid A. Liquid A is evaporating into the gas B. Here we have gas B. Now let's assume that there is a device that maintains the liquid level at Z equal to Z1. At the liquid gas interface, the gas phase concentration of A, expressed as the mole fraction, is XA1. This is the gas phase concentration corresponding to the equilibrium with the liquid at the interface. Here we have a gas stream of A and B. The gas stream has an A concentration of XA2. The gas stream flows slowly past the top of the tube to maintain the mole fraction of A at Z equal to Z2 is equal to XA2, and this value is constant. We can also assume that gas A and B is ideal, so the entire system is kept at constant temperature and also kept at constant pressure. Now our task is to determine the mole fraction profile of gas A between Z2 and Z1. What is the XA profile? Okay, the first thing we have to do is to write the shell mass balance. So we have mass of A in minus mass of A out plus the rate of production of A by homogeneous reaction equal to 0. Please note in this case we don't have homogeneous reactions, so this part is equal to 0. Yeah, this part can be cancelled out. So now we have to write what is the rate of mass A in. First we have to draw the control volume. This is the control volume. So here I have NA in at Z and NA out at Z plus delta Z. So rate of mass of A in is NA at Z times the surface or the perpendicular cross section minus the NA at Z plus delta Z. This is the A out times this perpendicular area equal to 0. Please note that NA is the flux of A. So to have the rate of mass of A, we have to times the flux with the surface. Okay, now we can divide this equation by S delta Z. And we get dNA per dz equal to 0. Okay, now we have to remember that NA is the total rate of A. Okay, so we have to find out what is the relationship between NA and JA. So I can write like this. In this case, we have to remember that A is the gas and B is the, A is the vapor and B is the gas. Please remember that the gas is stationary. Okay, so NB and b equal to 0. So at last, I will have NA equal to JA times, divide by 1 minus XA. Okay? So last time we have NA equal to JA over 1 minus XA. Please remember that JA is minus diffusivity of A, B times the concentration dXA over dZ. Okay, that's JA. So NA is all of this divided by 1 minus XA. Okay, let's substitute this equation into I think I forgot the minus over there. Okay, equal to 0. Now what we have is minus d per dz times minus dAB C over 1 minus XA times dXA over dz equal to 0. As the gas is ideal or can be assumed as ideal, so at constant pressure and temperature, the concentration must be constant as well. And the value of diffusivity of AB basically almost constant. So everything can go out of the bracket. So now I have dAB C d per dz dXA over 1 minus XA dz equal to 0. Okay. Now the diffusivity and concentration is a constant, and I can move it to the right side to get this equation. D per dz dXA over 1 minus XA dz equals to 0. Okay, the first integration for this part will give us dXA over 1 minus XA dz equal to constant 1. Okay, next we have another integration. It will give us C1Z, Z plus C2 equal to ln 1 minus XA, put minus in front. Okay, so this is our final equation about the profile of XA over Z. Now we need the boundary condition. We need two boundary conditions. The first one, at Z equal to Z1, XA is XA1. The second boundary condition is at Z equal to Z2, XA is XA2. Okay, now using this boundary condition, you can solve this equation and get the final equation to determine the XA profile over Z. That's all for now. Thank you and see you in the next video.